Okay, thank you very much. I would like to thank Vlad for the invitation. And in fact, it's almost embarrassing to say that as a probabilist, and you see I'm already quite senior, that this is my first visit to Russia. And I'm very pleased and very impressed by the beautiful city of St. Petersburg. So the subject of my talk, the random conductance model. So what I would like to do is in fact give an introduction on the topic. I will not go much into detail because I've been warned that this is a general colloquium for general audience. It's, by the way, a joint work with two postdocs, Sebastian Andres, he's in Bonn, and Martin Slovicki at TU Berlin. So let me first start with something rather classical and I hope well known, which is just standard random walk. So a random walk. What is it? So I will denote by xn a stochastic process. So xn says the position of the particle at time n, the time being discrete. Now this walk is a Markov process which jumps on ZD, on the d-dimensional lattice. Actually, we can make it much more general, but let me just start on ZD. And according to it's a Markov process. And you're characterized by the following picture. P is a probability that at time n plus 1, that you find the particle at location y, knowing that at time n, the particle was at x. So suppose you are on the d-dimensional lattice. Of course, I will only draw it in dimension 2. So at time n, you know it's at x, and you want to know what is the probability of finding it at y. So typically, but not all the time, we will actually take a very simple case where you only jump to nearest neighbor. So this probability is given by a transition probability, which is called by P for probability from x to y. So of course, P of xy is just a probability, so it's larger than 0. And it has a property that it sums up to 1. So basically, you start with a particle at some point, you jump, and you jump, you jump, you jump, you jump, you jump. So this is how you can define a random walk. And if you want to have one model in mind, keep it for quite some time, so just consider what is called the simple random walk. With the following property, just jump to nearest neighbor. So P of xy, it's 1 divided by 2d if you are a nearest neighbor, and 0 elsewhere. In particular, you don't stay put. So you just jump. So what the particle is doing, he's looking at his neighbor and decide with the same probability to which of the neighbor he wants to jump. It looks like an extremely simple model. Let's assume for simplicity that you have no drift. In other words, there is no trend where you want to go, which means in the following sense. So you look at E, P, 0, E. So this would just tell you what is your preference at time n, where you want to go. Suppose you have no preference, 0. So there's no drift. So basically, on average, the random walk stays where he wants to be. Then there's a very famous result of Deuschel. You have a so-called diffusive behavior. What does it mean, diffusive behavior? It means that basically the scaling is the following. If you wait for sometimes, let me draw here a picture. So this would be a 1D model. This is the time. This is the space. Typically ZD or Z1. So you look at the walk. Usually people interpolate between. Of course, it should be time discrete, but you interpolate in between. So the diffusive scaling tells you that you have to rescale time much faster, so by 1 over n squared, and space by 1 over n. So diffusive behavior tells you the following. Let me denote by xn of t. So I divide the space by 1 over n, but I speed up the walk. So I just look at time n squared t. So this would just be the integer, which means, again, the time is rescaled much faster than the space. You look at this object here. Then as n tends to infinity, this converges in law to a continuous process which is called the Brownian motion. So a rescaled Brownian motion. So you have a scale, you have some matrix, the non-degenerate matrix, Bt, where Bt is a so-called Brownian motion. The Brownian motion is, if you wish, the prototype of a diffusion. I will explain you a little bit better. By the way, I forgot to make an assumption which is important for this. You will believe that if you go along, so you look at this location, you want to jump from x to y, and then you look much further. So this is x plus z, and you want to jump to y plus z. So we'll assume first it is homogeneous. So the translation invariant or homogeneous case you would say that the jump probability from x plus z to y plus z is the same as p of x, y. So if you move things along, you still have the same transition mechanism. So typically for the simple random walk here, this is the same. Now you comment, so Brownian motion. So Brownian motion is, if in a way, the prototype of a homogeneous diffusion. So it's a continuous process. So Brownian motion is continuous. This is one aspect. It is memoryless in the sense that if you look at what you will do in the future, knowing that what happened in the past, then it doesn't matter. So we can phrase it in the following way. You look at the future. This is the future. This is the increment of the future. What you do, you arrive at beta s, and you want to know what is going to happen in the future. This is independent of what happened before. The past would be the trajectory before time s. So you have this renewal property. So the Brownian motion, in a way, goes around, and then when he's here, he just starts and then he just forget everything where he has been. And finally, what is important for Brownian motion, you know that a stochastic process, any process, random process, depends on the distribution. So you want to know what is the distribution. So what is the law? What is the distribution? So the law is Gaussian of, let's say, an increment, beta t plus s minus beta s. So for s fixed, is the Gaussian distribution with identity and times t proportional to t. So what is the Gaussian distribution? People have seen this. It's just the Gaussian law. This is the Gauss curve, which looks like this. And the point is here, this here is of the order square root of t. This is the Gaussian distribution. So this is the prototype of a Brownian motion. So basically what I'm telling you is you start with a discrete model on the lattice. You assume that you have space homogeneity. So in other words, if you move things around, you see the same thing. Then you end up with a Brownian motion, which is this object here. By the way, the Brownian motion, it is quite interesting. It emerged in mathematics. I mean, the first rigorous proof of existence of Brownian motion, that there is a measure which has this property here, was due to Norbert Wiener. That's why it's called the Wiener measure. But from the viewpoint of application, there are two people we almost at the same time introduced the Brownian motion. The first one was Einstein in his famous 1905 paper on the Einstein relation, which is the diffusion, and at the same time Bachelier in France, and for the curve of a stock exchange. In other words, in finance mathematics and in physical, Brownian motion plays an important role. So this is the first thing I wanted to explain. So maybe what I wrote here, okay, seems a bit artificial. So this is, of course, for the few, I mean, I will want the few probabilists in the audience. It's clear what we mean by a weak convergence of this. But let me tell you an application. So what is behind this symbol here? And the best application you can think of is the following. So the relation between probability, this is just in the probabilistic language, and I'm going to switch to PDE language or to harmonic analysis. Just to give you a motivation why this type of convergence is relevant. And the idea is the following. And what I'm telling you is really applied for numerical scheme and so on. So you take some domain. So this is a domain in RD. And now I'm going to look at a mesh, which has become smaller and smaller. So guess what? The mesh here, so I'm going to discretize. So discretize by 1 over n. So let me denote by dn, which is 1 over n d, sorry. It started intersect zd. So you have just discretized things. And then you let your random walk, now this is the 1 over n scaling. You let your random walk jump here. And now what I'm looking at, find a harmonic function. You give yourself at the boundary of the domain, which is outside here, a boundary condition. So here I'm going to give f. So you want to find u from dn to r with the following two properties. The first property, that inside it is p harmonic. P harmonic in the following sense. You look at the sum over y neighboring of x, so this symbol y neighboring of x, of p x to y, u of y minus u of x equals 0 inside. Second, you would like at the boundary of this object here, you want that u at the boundary take some value f. So think of this as being the Laplacian, for instance. That's why we call it harmonic. So just suppose you want to find an harmonic function, but this kind of discrete harmonic function, with a given boundary value. Then it turned out that the probabilist can solve this, which means you could use Monte Carlo techniques to implement it, is the following. You start by E, its expectation. Actually, in Russia, I should put an M, I guess. You start a random walk at x, and you wait until it exits. So you look at tau. So tau of dn is the exit time. You wait until the random walks exit the domain, and you just evaluate the function at this exit time. So again, you start your random walk, you sample your random walk, you wait until it exits the domain, and you evaluate it here. Now it turned out that this will converge as n to infinity, so maybe I should put the n here, to the corresponding function here, where instead of having p here, I just have the Laplacian. So we just told to the harmonic function to this. So this is one of the applications, and that what you have to realize in what I wrote here, and I guess, is in some sense all what I'm telling you is that you can visualize the solution of this boundary problem in terms of the expectation of a function of the random walk. But what is irrelevant in this business is that it's a function of the trajectory. And this is why this type of results are of relevance. I didn't stress it maybe enough. Here I'm really saying that not only at a fixed time, but along the trajectory, the distribution of the trajectory of this particle converge to the trajectory of this. And you see here, some sense, what I mean here by here at fixed time, because here I look really at this time here, which is not a fixed time. So you need along the trajectory to get this. So this will converge to u, solution to Laplace u equals 0, and u on the boundary equals f. So this is the harmonic function. So you will pass from the discrete one to the continuous one. You can also change a little bit. Let me just, for sake of time, change a little bit. So this is this solution of, let's say, harmonic function. And as you might know, this can be represented in the following way. You give yourself an electrical charge at the boundary and you want to know what was the electrical part in the center, or the same in physical terms. You can also think of the heat equation. You put a heat distribution at the boundary and you want to know how it looks in the interior. You could also look at a similar question, which is the Poisson equation. So we could by V of dn to R with the following property. First, the discrete equation. Now, instead of being 0, you give yourself, to put V here, some value g of x, and at the boundary you put it 0. Then you can also represent the solution here in terms of an expectation. So V, you put an n here to stress of x. Well, you start at x, and then you sample along. You put the sum n equals 0 until the exit time of g of x of n. So again, you can do the same kind of game, but you, instead of waiting until you exit, you just sample along. This is until you get out. This is the solution. This is how you could, in some sense, with a Monte Carlo technique, simulate this to get this, and then it will turn out to converge to the solution of minus Laplace v equals g and v at the boundary equals 0. So this is one of the reasons, one of the motivations why one is interested in this type. This result is very famous. It's called Donsker invariance principle. Invariance principle. This is why people are interested in this type of result. And there are lots of papers about it, with, in particular, knowing how fast this converges and so on and so on and so on. This is not what I would like to discuss. Now, before I want to proceed, let me just tell you an easy extension of this type of result. And there's a lot of literature about it. For instance, in the book of Strup-Varadhan, which is the following. Here, everything was homogeneous. What do I mean by homogeneous? As I told you, suppose you look here from x to y to nearest neighbor, and you shift it from x plus z to y plus z, you had the same transition mechanism. Well, you could think that this is changing in space, but smoothly at scale 1 over n. So all what I'm saying is that suppose that this region here is divided into different regions. So here, for instance, I would have one transition mechanism, and here I would have another one, and so on. So piecewise constant. You change it, but in a smooth way. In other words, what you want is that of the order 1 over n, you get the same thing, and then to the next one, then to the next one. Then it's easy to adapt this, and instead of getting just a homogeneous Laplacian here, you would have a colored Laplacian. In other words, it will depend on the location. But I want to stress this is if things change smoothly. Okay? And like I said, there's a lot of literature on this type of technique and how to implement it. Okay. Now, today, in fact, in the random conductance model, this is the title of my talk, what we're going to do is, instead of having this rather smooth or just invariant, translation invariant mechanism, we want to have a very disordered media. In other words, a transition which is very random itself. So the random conductance model, and I will show a picture soon, the picture is radically changed. So you are in a setting which is called a random environment. Or also in mathematical physics in so-called disordered media. Where the transition probability here is itself random by some external randomness. So in other words, what we will have is that instead of having p of xy, we have now a random variable. So the transition itself is random. So I'll put a p of omega of xy. And typically what you would choose is that this guy here has the same type of translation invariance that we have, but in terms of the randomness. So what you have is the following, that P omega x plus z to y plus z is as if you have shifted the environment, but you have to shift the environment by z. So you just shift the environment by z, and of course shifting the environment means that it's not constant. And what we will assume is the following. So let me just take, in the conductance model, actually the transition is a very special form. We have it in the following way. So P omega of x to y is an omega of x to y. You want this to be a probability distribution. So this is divided by z neighbor of x of omega xz, where, and that's going to be quite important, omega xy is in the conductance. So the rate at which the walk jumped from x to y is symmetric, the same as omega to y to x. These are all the conductances. And maybe the favorite media people think of, so you have to put, if I put an omega here, this is external. This means external. You see, there's a complication in the whole business, and that makes it that the first time you look at this type of problem a bit delicate. The subtlety about this problem, I start with a random walk, which is itself a random motion. So you start with a random motion. But now the random motion depends itself on some other randomness, or if you wish, exogenous, from outside. This is the external randomness, which dictates the random behavior, if you wish, of the walk. So the random media, let me just take this example. So because we are, we're fortunate to be in Russia, so of course if you think of probability, what you would like to is define a probability space. Probability space, which is the space where you would define your random conductance. So omega is going to be R plus, because they are non-negative, to the power ED, where ED are the bonds. So ED are the non-oriented nearest neighbor bonds. So it's x, y, so that x minus y equals 1, and x and y are in ZD. So I take this product space. So I decide at each bond what is the distribution. Then I take just the product sigma algebra. And then I take a distribution P, which is of the randomness on omega. And a lot of what I'm saying was first discussed in the IID case. For example, IID, which means that basically, I will draw a picture and I show you more. What you do, you define randomness. You decide at each bond what some kind of distribution, for instance, like this is going to be large, this is going to be small. Suppose you only take two values, large and small. That would be, I will show another picture. So basically, you just cross a coin. For instance, you have only two randomness, either large or small. This is a large. You decide this is going to be a large connectivity, this is going to be a small one, and you just decide at random, which means with the product rule, it would be IID. In fact, for what matters for us, we will go beyond IID, and there are two things you should use if you don't do IID. First, the law itself should be invariant by translation. So P is the same as P. So if you shift things, you have the same law. It doesn't mean that they are frozen, but they shift law. This is translation invariant. This is one thing you want to make. So you want to look that in law they have the same. And the second point, you want it to be ergodic. So there are two ways of defining ergodicity. For a probabilist, it's easy. Or someone working in dynamical system, it just means if you take a set A, which has the property that it's A, x minus 1, then the probability of A should be 0 or 1. So this is the abstract definition. But I realize that if you write this the first time to a non-probabilist, it's not clear. By the way, this means that the set A must depend on infinitely many coordinates because it's the same. So this looks like, I mean, in my view, this is not the adequate way of all. This is a standard way of defining what ergodicity means. But think of the following, and that's even more important. Ergodicity is equivalent with the following fact. If you sample in a big box, so I take a big box of size n, so Bn for me is always a box of size n, and then I just count how many of the, how many times can I find my shifted configuration in a set A, so A finite. So some set, sorry. You just take some set and you count how many of these shifted are here. This is, if you wish, the space average. You just make an average over the space. Then ergodicity means that this converges P almost surely to the probability. So you can think of the following. Ergodic just means that if you make some spatial average of the process, then you end up here. Okay, now let me show you a picture now of one of the special media which has attracted a lot of attention. So until this warms up, I can say a few words before I proceed. Okay. Very good. So maybe if you could even though thank you. I don't have a pointer, but I have a stick. So what I show here is an environment which just consists of holes. So I decide, so here this is actually a picture done by a co-author of mine, which is Martin Barlow at UBC, which look at the following environment. You decide which of the connections are open or closed with probability P. P being larger than 1/2 here. So what the black region here is the holes. If you have a hole, there is no way for the walk to move to this region. So the walk can only be confined on the blue. The blue one are where the connections are open. And what I'm showing you here is the so-called heat kernel. So you wait for a while and you ask yourself, what is the density? So I start with a random walk in my environment. It can only jump on the blue. On the blue, this is a lattice for which there are connections. It cannot jump where there's dark region. Now, in yellow, it means that's where you will find the random walk very frequently. So this is a distribution. On the red, it's less frequently, and this is now. So this is, you wait for a while and you decide, well, the random walk will be more or less confined here. So this is the heat distribution, if you wish. This corresponds, that's why it's called heat kernel. It's the heat distribution you would measure for such a lattice after short times. So it started here, so it didn't spread really. Now let's proceed. This is after short time. This is intermediate time. So the time has already grown a little bit. And you see the heat has spread out a little bit. It invades a little bit the lattice. But you see, it cannot do it in a homogeneous fashion because there are lots of holes. Now we keep doing it. This is intermediate time. Now the time becomes larger and larger. This is after larger time. It invades more and more, if you wish. This is a heat distribution after larger time. This is after even larger time. And finally, after a very long time, this is how it starts to look like. And if you're familiar, and this is after a very long time. Now, of course, this is extremely detailed, but maybe if I take off my glasses and I sit in the last row, this will eventually, if you're very far away, you will not recognize the hole because these holes are finite size. They are small if you go very far. So if you rescale things like I did, which means at a diffusive scale, then this starts to look more and more like a Gaussian distribution. Of course, if you look at this here, because there's so much detail, it doesn't look like a Gaussian. Gaussian, remember this Gaussian bell curve I just showed you. But basically, this is what is going to happen. So this is something very special going on. Although the media has a lot of singularities, what do I mean? It's very irregular. Still, at long scale, it starts to look more and more like a Brownian motion. And this is precisely the object we want to do. This is what we'll call the quenched invariance principle. That means you give yourself one of this lattice, one of this environment, and for fixed environment, if you wait long enough, the behavior of your particle will look more and more like a Gaussian one. So maybe I proceed now with the blackboard. So you can put the lights on. I don't need the projector anymore, thank you. It was just for illustration. So
basically, is it true that the total area of the percolation cluster goes to 1, the fraction?
No, of course you pay a little price. The proportion is not 1, but the proportion is fixed. So it's going to be a it's going to be a Brownian motion with a rescaled. The rescale comes exactly from the density of the cluster.
What restriction do you impose on your distribution of the
conductances? I will come to that. This is a very good question. So let me do it again, and we'll come to that, and you will find out. And I will explain you why you need some conditions. So again, what I'm looking for is what is called in the literature quenched. Quenched means P almost sure. You give yourself the environment once forever. You sample first the environment, and then you let an invariance principle. So this is abbreviated with QIP. Now I'm in Russia and not in the Vatican, but if you were in the Vatican, you would see what QIP could possibly mean. So it's the following statement: for P almost all environment omega under P omega 0. So this is the law of the random walk starting at 0. So this is the one with the environment omega. Basically, I can show it again what I mean. Just saying that the transition is given by this, by the random conductance model. So what we have is P omega from x to y is omega x to y divided by the sum. And of course, I want to, the basic ingredient is that it's symmetric. So what you would like is that you look at the rescaled object. So you rescaled by 1 over n the space and by n squared the time. You want this to converge in law to a Brownian motion. And that is it, where what you want is that sigma, which is actually sigma of P, is deterministic and non-degenerate. Deterministic it depends on the distribution, but it's not a random variable. Now to go back to your question, what do I have to assume? Before I, how could we raise this?
Just look down.
Again, I see. Okay, thank you. Now, if you think of what is going on, there's a problem here before I continue. The problem is the problem of trapping. So we need to go back to your question. Okay, I assume that P was ergodic, but you need some moment condition. And I will tell you what moment condition we have before I state the theorem. The problem we have is trapping. What is a trap? I'm going to draw a trap. Trapping, I don't know how you say in Russian. It's a country of hunters, so they should know. What is a trap? Let me show you what I mean by trap. Suppose that on the lattice you find something like this. I'm just doing it in 2 dimensions. So this is the connection, very large and very small. So what I mean is the rate at which you jump, this is a point, let's say x. So omega x plus E1 is very large. On the other hand, all of the others, omega x plus I, so these are this connection in here, is very small. And the same here. So here you can jump back, because this is the same as, of course, you remember, the same as, because it's symmetric, you can jump back very strongly in this. So what is a walk going to happen? When it gets there, well, he has to decide where to go. With very large probability, he will jump here. Once here, he will jump here. Once here, 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 here. And it might take so much time to do this that he never escapes. So you have to be careful that this does not happen. And now I can state the theorem. This is a theorem that we have got with Martin Slovic and Sebastian Andres. And I will tell you more about the literature. So theorem. Say P is ergodic. So we have a random conductance model, and then we have the following moment condition. Expectation of omega E, or B, sorry, B for bond, to the P is smaller than infinity. Expectation omega B to the minus Q. So you see, trapping can take place in 2 different, you have 2 dangers with trapping. Either it could be that this is very large with respect to the other, or it could be that these are very weak. So I want to make sure that this does not happen. With 1 over P plus 1 over Q smaller than 2 over D, as you call a PQ condition, then the quench invariant principle holds. Actually, we showed more. We can even prove that local CLT takes place, and we can prove that this is necessary for local CLT. But I will not go into detail today, but we can even prove local CLT, and this condition is sharp for local CLT. So if you just look at the heat kernel, if you want the heat kernel to converge, you need this. So again, this in a way tells you that you avoid the trap. The trap cannot be too serious if this condition is satisfied. Otherwise, it could well happen that basically the random walk gets to a place and doesn't move anymore, and then you cannot expect to have a Brownian motion at the end. Okay?
So you mean it's killed by the normalization?
Yes, because 1 over. Now, maybe just some reference. It turned out that if you're not interested in the quench, quenched is an important. Quenched means for P almost all. So it means that for the experimentalist, and that's important, there are 2 ways. And for the experimentalist, it means the following. The experimentalist is going to cook up one media, so he generates a media, and then he looks at the walk for a long time on this media. This is quenched. Now, sometimes experimentalists, they don't cook up one media, but they repeat. They make one media today, second media tomorrow, and so on and so on. And then they take the average over the media. So the first result in this business in the average sense was obtained by Kozlov. And this was already in the 80s, and by Kipnis and Varadan. And here what they actually use is P equals 1 and Q equals 1. You see we are off. This is more stricter. If you're not interested in average but in the quench case, so that was in the 80s. 80s of the previous century. It took about more than 20 years, 2000 of, by Vladas Sidoravicius, and I think Vladas should be well known because he also co-organized this summer school last year, and Alain Solznitzman from ETH Zurich, the first quench case, but in the uniform elliptic case, which means it's bounded from above and below. See, if it's bounded from above and below, you don't have the problem that you might get stuck. Recently, and this is very special for dimension 2, Marek Biskup showed that in P equals Q equals 1. Actually, this is known to be necessary I mean, this condition is known to be necessary in this case. So basically, our improvement is for higher dimension. And like I said, our improvement also shows, here it was not showing local CLT, that it's also good for CLT. So basically the literature. Before I proceed, and I promised not to focus too much to maybe random walk, which is a typical toy model, let's say, for probabilist, I want to make a connection to PDE. I mean, you told me that a few people here work in PDE, on mathematical physics. And there is a link I tried to show you with the Brownian motion between PDE and random conductance model. And the link goes via diffusion in divergence form. So there's a nice link between the two. In some sense, the random conductance model is nothing else but a discrete version of diffusion in divergence form. So diffusion in divergence form. So diffusion in divergence form is probably the most one of the most studied model in PDE, which is the following. So instead of looking at a discrete model, I look now at a time continuous model, so on RD. And the diffusion has a generator which looks like this. LF of x is going to be a divergence, the sum over I equals I and j, 1 to d, d dxi, aij of x, dxj, f of x. So it's a diffusion in divergence sort where aij, for simplicity, it's a non-negative symmetric matrix. Maybe the best, if you look at this, and this is why I would explain you the connection between the random walk and this. So I claim that what we're looking at is a discrete version of this. And the best way to understand why is to look at, you know, the big challenge in defining such a diffusion is when the coefficients here are non-smooth. If they're smooth, classical theory will get it. Just classical, I don't know, I'm sorry. Again, a Russian. Anyway, there are some very classical techniques to get it done. If they're non-smooth, then it starts to be hard. And it's only going to work because you use the symmetry here. So typically, you don't know how to solve this a priori, but what you will do is integration by part. So you look at the following quadratic form. You take some test function, nice text function, let's say g. You put minus LF. And this is just a scalar product with respect to the Lebesgue measure. So this is a scalar product on RD with respect to Lebesgue measure. So you integrate, and then you make an integration by part. So you bring this on the other side, and what you end up having is a Dirichlet form, which is just the integral on RD on aij of x, dxi of j, dxj of f. So this is just an associated Dirichlet form. This is how basically the technique you use to prove existence solution of this equation. Now, if you look at the corresponding Dirichlet form, for the random walk, then the Dirichlet form of the random walk, you also look at this. So you just put the generator of the random walk, you just put the counting measure instead of the Lebesgue measure, then you will find out that the Dirichlet form looks, usually people put an E, this is just a notation, E of G and F. And by the way, you see here better why this looks like, it wants to look like a Brownian motion. Why? Because if the matrix is nicely behaved, you could think of the identity matrix. You get up just the standard Dirichlet form for the Brownian motion with the Laplacian. Now the corresponding Dirichlet form for the random walk is just going to be the sum over the bond omega b, and then what you have is a discrete gradient. So it's just a discrete gradient. So where bond is just a bond going from b minus to b plus. This is the corresponding Dirichlet form. So if you do for the random walk, this is the analytical object you have. And for the diffusion in differential form, you have this. Now, all what I'm telling you can also be done for random. So I'm going to put a random guy. Put omega here. And of course, I assume at the same technique that a ij of x of omega is the same as a ij. You shift your environment by x, and you look at 0. And you take a p, which is ergodic. And then what the theorem is the following. You look at the smallest eigenvalue. So let me denote by capital lambda the largest, and by little lambda the smallest eigenvalue. In terms of eigenvalue. So exactly the PQ condition. So you want that the largest as a p moment and the smaller one as a minus q moment with the same condition. Then the quench invariant principle holds. So you could also do the same kind of technique, but for the continuous model. The reason why I'm stressing this is very recently, also a Russian mathematician, Zhikov, who is really one of the experts in homogenization, got exactly the same type of result we have. He was not interested a fortiori for the quench invariant principle, but for heat kernel estimate. So for so-called heat kernel, it just showed that the transition kernel of the diffusion, so I don't know how you write Zhikov in Russian. I hope it's correct. Zhikov just proved that you have heat kernel estimate. Heat kernel estimate means that basically the heat kernel looked like a Gaussian estimate exactly under this condition here for this type of model. Okay, now I see that I don't have much time to give the proof, but I want just to say a few words about the proof. If you, I have, how much time do I have? Maybe 5 minutes, because
10 minutes.
10 minutes. So this is a relation with PDE and the nice paper of Zhikov, which has exactly the same condition. So what about the proof? What is interesting in this model, is the proof relies on two types of completely different arguments. So the proof. The first part is a purely probabilistic argument. Probability. But already in the probability we use analytical tool, which is one magical word in probability, which is martingale. So martingale plays a big role in the probability part. And in terms, if you don't know what a martingale is, for probabilists you know what it is, what I would just rephrase it for an analyst, harmonic function. Actually, in this setting, it is called harmonic coordinate. So So basically what you do, let me just very briefly show you what I mean by this, is the following. You want to rewrite x, which is the coordinate. X is the coordinate of your work. You separated the term, the summation of two, one which is psi of omega and x plus chi of omega and x. So where psi and chi are from omega cross zd to rd with the following property. They satisfy what is called a co-cycle property, which means that if you look at increment, for instance, of psi, x plus z minus, if you look at the increment of this object, is the same as if you just shift the environment by z. This is so-called co-cycle. The second property is that psi is harmonic. Psi is p harmonic, p omega harmonic, which means that the sum over y neighbor of x of p omega xy psi omega y minus psi omega x is 0. So you can find one like this, and the other one would just be the difference. Now, it turned out, if you have these two properties here, it turned out that if you look at xn, but in fact we don't look at xn. You remember we have to speed up by n squared. So I put, and I have to divide by 1 over n. Then we write down, this is 1 over n psi omega xt n squared, sorry, plus 1 over n chi omega xt n squared. Now, harmonic means that if I look the process, I put a m for martingale, which is just psi omega at xn. This is a martingale. In a way, okay, for probabilists it's clear. For non-probabilists it's just a function of an harmonic function. What is a martingale doing? A martingale is an object that he looks at his past and he has to decide where to go in the future. And it's conditional expectation, so his revised opinion for the future is null. If you wish, it is at equilibrium. There's another very famous, again, of a famous Russian mathematician, which is Cohort, Embedding Theorem, which basically tells you already that every martingale wants to be a Brownian motion if you make a time change. Every martingale wants to be a Brownian motion if you make the adequate time change. And basically, the Ergodic Theorem, which I will not go into detail, will tell you that this martingale here is already almost what you want, because it's a Brownian motion with a time change. You can control the time change so that this part here converges to the Brownian motion. So again, by Cohort embedding. So this part, because it's a martingale and you can control the time change, will end up to be a martingale. You still have the problem with this guy here. This guy here, by the way, this psi is called the harmonic coordinate. Why it's a harmonic function. This guy here, which is not harmonic, is called the corrector. So of course, if you look at your process, it is not a martingale because you have to correct it with the corrector. And now this is the second part, which is the analytical part, and I only need 2 more minutes. It is the analytical part, which says you are going to prove that the corrector plays no role. So what you want to prove is in fact that 1 over n chi omega x t n squared goes to 0 П.Л.Чебышева when n tends to infinity. In fact, because of the martingale, you know what the martingale just behaves diffusively. So this is enough in order to prove this. It's enough to prove what is called the sublinearity of the corrector, which means that you take 1 over n, you take the maximum x in the ball of radius n, of chi of omega x, then this will go to 0. This is sublinearity. Sublinearity of the corrector. And it turned out that here we need analytical tool. So the first thing you're going to prove, so this is a challenge. This is the reason why, by the way, this property of П.Л.Чебышева, the reason why it took about 20 or 25 years to go from Koslov, which is just on average, to the quench part. And the idea what you're going to do here is the following. I mean, the first thing which is easy, here I take the maximum. Suppose I give myself one direction, which is 1 over n chi omega n times ei, just in one direction. Now you can write this as 1 over n and the sum of the increment. You look at the increment, but the increment, you remember, was chi of tau k by the cocycle property ei, just the cocycle. You just look at the telescoping sum. And here what you use along is just the ergodic theorem. This converges to the expectation of this here, which is 0. So this is easy. So this is all what I'm telling you is, if you look along one, you see, maybe let me draw a ball. So if you go along here or along here, then everything is fine. But you want it uniformly everywhere here. I'm almost done. From there, it's also easy to get it in L1. In L1 means the following. I look at 1 over n. This is the normalized 1 norm. So what is it? It's 1 over the size. The 1 over n comes from here. Sum over x in the ball. And I take the L1 norm. This is also easy. It's just an iteration of this. You iterate this. In other words, instead of going one line, you go this way, and you go this way, and you go this way, and you just spread everything. This is in L1. And now I'm almost done. What you really want is, instead of having the 1 here, you want to have the infinite. You want to have the infinite instead of the 1, because this is the definition of the supremum norm. And here what you use is Moser iteration. This is a well-known tool. This is a well-known tool which allows you to control solution. Here it's a solution of the Poisson equation. Moser iteration will basically tell you that if you look at the norm, and here I put r times alpha, this is going to be smaller than a constant 1 over norm of alpha, and importantly, it can only work if r is larger than 1. So you start with this, and then you can iterate this. This is behind Moser iteration. And Moser iteration relies, this is for the solution of some Poisson equation. And Moser iteration relies, in fact, on Sobolev inequality. And I'll be done with this. Let me allow this just a second. The key ingredient in proving such a thing is the so-called Sobolev inequality. Again, a Russian mathematician, of course. And that's, of course, the key ingredient. You see, I have this very strange condition. 1 over p plus 1 over q smaller than 2 over d. And people familiar with PDE will say, somehow it smells like Sobolev. Why? Because the dimension comes into the game. And the Sobolev inequality we have, in fact, it's a weighted. It's the following, just to finish things. You take some function u with a compact support in some ball. I would put here some norm. Now you look at, let me put u square. I put a r here, bn. This is going to be smaller than some constant. Then I take the weight omega. I take the p norm weighted in the ball. I take the minus q norm. I put a -1 here with a q. And on the right-hand side, I have the Dirichlet form. So which is the sum over the bond in the box, omega e, and then it is the discrete gradient square divided by the size of the box. So what does it mean? On the left-hand side, you have some norm, and where r depends on d, q, and p, is d minus p divided, yes, d divided by p, d minus 2 plus d divided by q. So this is the weighted Sobolev inequality. It's weighted why? Because here you see you have this weight here. You have to take care, and you have the weight here and here. So you have to be careful. And this is basically what you get just by Hölder's inequality and standard Sobolev inequality. So standard Sobolev inequality with a little bit of Hölder gives you this here. So you have one weight here, this here. And the nice thing is this is exactly larger than 1 if and only if this condition is satisfied. And Zhikov has also realized this, also used this in his proof. So basically the key ingredient is Sobolev inequality. Once you have Sobolev inequality, then you get it. And the only difficulty is to make sure that they are weighted. And now you see what the condition comes in. By Ergodic theorem for the specialist, this converges to the expected value because it's a normalized norm. So it's finite. And this converges also to the expected value, which is exactly the condition we made. So this, when the box becomes large, tends to this and this. And I'm done. Thank you for your attention.
We have time for 1 or 2 quick questions.
When we consider discrete model, it's obviously, I mean, it was done by Donsker, you said that this passing to limit, yeah?
Mm-hmm.
But you could do this random stuff already in the in continuous model, like
Sure.
you have RD and
Sure.
so what could you say?
Okay, sure. So basically, what you could do is, of course, instead of having a jump process on the lattice, you could be considering a jump process in RD. Okay, and then you have to control the jump intensity. There are some technical restrictions. First, you have to make sure that.
I mean, you already could consider a Brownian motion controlled by some, I don't know.
Oh, this is exactly what I said. This is this, by the way, I forgot to mention. This is a joint work with Chiarini and myself, which is a diffusion in divergence form.
Okay.
So the diffusion in divergence form, okay, with the eigenvalue, you remember? So I have a diffusion in divergence form, which is nothing else but the transform Brownian motion, if you wish. If you have the moment condition, then you can get it. And this is what I did with Chiarini. So you can start with the continuous model, which is just a diffusive. You have to control the eigenvalue of the matrix. So the generator is of the form sum over ij, d dxi, some matrix aij of omega of x, dxj of f of x. What is very important is that this is, again, a symmetric model. Because the conductance is also the property that it's symmetric, okay?
Now let's take the speaker and continue at a small reception.